Today I'm going to show you exactly how to build and simulate real automation systems from scratch. The kind that runs factories, drive production line, and puts you in the top percentage of builders in the industry. For decades, this kind of skill set are tucked away. The people who knows it guard it like a treasure. Not because they are selfish, although not all of them, maybe a few, but because in real world project timeline can sometimes be brutal. There is no time to slow down or take a pause or teach. So when factory or automation house is on deadline, everyone is focused on getting the system up and delivering, not training the next person. So I've seen it firsthand in over 2 decades of industrial automation. Now knowledge ends up staying with those already doing the work, while everyone else left without a clear path to learn. But today, that is going to change. I'm going to break that cycle. You are about to get a rare look behind the curtain. The kind of insight no YouTube channel, no university degree, no training boot camp will ever give you. I know that's a bold claim, and here is why. This isn't theory. This is exactly step by step thinking, problem solving, process, and practical software and hardware skill that delivers system that worth six, multiple of six, or even in millions of dollars. In this tutorial, there is no expensive licenses. And most importantly, you don't have to have permission to learn. You own it. So if you ever wanted to get hands-on with PLC-HMI programming and simulation, this is your chance. Grab a notebook, bookmark this video, set aside a time, and let's get into it. What is a PLC? It's a programmable logic controller. PLC is a rugged industrial computer used to control machine. That's it. Forget the long history. If you're curious, you can always Google it. Skip the fluff. We go straight into building our first machine logic using ladder programming, the most common method in industry. Of course, yes, IEC 61131-3 does include other programming language. We will touch on those later. But for now, we'll keep it simple and practical so you can simulate your real automation on your laptop fast. So generally these are some of the PLC you are looking at. There are many brands out there. So for this illustration, I'll just keep it simple. And what is an HMI? HMI is a human machine interface. Essentially, it's a screen that lets you interact with your machine. So like a car dashboard for automation. So we are not here to dwell on theory, we are here to build. By end of this, you will have your own working HMI connected to your PLC logic. You'll see how the virtual machine respond in real time. Okay, you can see these are some example HMI here. These are one of the brand of PLC. It has an Ethernet IP. It's operating under 24 volt. It has 24 volts input and 20 relay output. I'm going to show you this. Okay, this is one of the micro PLC from Allen Bradley. So it has Ethernet IP. It has 28 input point, which is at 24 volt DC or AC input, and 20 point relay output. It operates under 24 volt DC. It has 6 high-speed channel, embedded USB programming, all the good stuff. So I'm going to select this, and the HMI will be something similar to this. The HMI will be something similar to this. Okay, the one that you're looking at is a 4-inch type. Okay, the resolution will be depends what is your machine you're doing. So resolution comes into play. Then the connectivity and the operating voltage will be similar. 24 volt DC will be sufficient. So I'm just going to add this to the project. You can see it has these memories, all the serial
port you can set up, the communication, USB port, and then all this I/O input. For this model, you cannot configure the output because it's a relay output. For the input, you can actually choose what kind of input speed that you want it to detect. Normally 10 millisecond will do, or 1 millisecond will do, but this one are equipped with the high speed input. So if you have some sort of counting that you want to do, so you can do it with this. It's an actual other modules you can add in. So these are the PLC, the HMI, choose the landscape. Choose diagnostic. So the HMI will have these pages depending on what pages you are creating, like alarm banner or a diagnostic page. So this will be the screen. So this is just general about HMI.
Here I have images of PLC from National, Omron, Mitsubishi, Barco, Adlink. This PLC, like National or Panasonic, mostly will give you like one or two programming language. Mostly like in National or Panasonic will have ladder. In Omron will have script or structured text and ladder. Mitsubishi solely in ladder, but they comes with different IDEs, other languages also. For Vago and Erling, they support the five languages, so directly is suitable for the IDE that I'm going to show to you, suitable for this both model. Definitely, advanced programming can be done with this, but nonetheless, it's all in the coding, so it doesn't matter what language you use. No, there's a way, there's a method to the madness, how to use it, how to program it in a way that it doesn't crash, it's robust. Another couple of more examples for HMI. I didn't show you what brand it is. It does not matter what brand for this. Something that you design with your Python code, or you can buy a standalone. It could be from same brand, Mitsubishi, Omron, Prophase, Kians, all that brand, or you can buy industrial HMI to do this. You know, now it's very competitive at this moment. It's very competitive at this moment that you can choose any kind, any brand which is available, which is suit your budget.
The PLC HMI teaching platform is the one that I'm going to teach you. Is one of the powerful platform. To keep it simple, this environment I used to teach PLC and HMI. It's a professional grade. Lets you build, simulate, and visualize machine logic, just like a real system. We focus on what need to get started. No overwhelm, just real progress. And let's dive and start build your first automation logic. The quickest way to start writing your first PLC program. So this is the exact platform, real PLC automation. It's a powerful environment where you build, simulate, and see your logic come to life. You do not need to know everything right now. In fact, that's the point. You focus on what is essential and gets your first ladder program up and running. Do take note, I'll cover up all the different IC programming language to building fully functional logic circuit with context, function block, coils without needing physical hardware. Let's begin. So now we're going to write your first ladder program. I'm going to start a new project. So for this, you just select this, click OK. For now, you don't need to change the name of the POU and the language as LD ladder. Click OK. This is the canvas where you start writing your program. For this example, I want to show you how to do a start and stop button. You know, basically we use to start a process and stop the process. So let's start with adding a contact, and then right click. I'm gonna add a function block. Then I'm gonna use a rising trigger. Then I'm gonna put in an output. I think it's gonna put in a or. So I can just drag this thing in. Maybe I'll explain to you later why are we doing this. Then we add another network, which is essentially another rung. We add a contact. Then we can copy this, make it quick. Then we're gonna put in output. Okay, so we're gonna now we already have some of the building blocks here. Yeah. Okay. There's one more things I need to add. Okay. This is simple start-stop code. You can use, there are many ways to do it. I'm showing you one of the way. Okay, so now we can start adding the tags. So for this, I'm just gonna call it start PB. So just select as a variable, then it's a boolean. For this, you can call it start pulse short. So it's a rising trigger variable. Okay. For this, I'm gonna name it start code. So a boolean, what we do is we copy this, paste it over here. Okay, for this is the stop push button. Just choose boolean. Then for this is a stop pulse. And we're gonna use it as a stop PLS, right? And copy this tag over here. So this is the simple latching, start latch, and this one will actually stop it. So this one will hold the latch, the start button will hold, whereby this one will cut off the holding circuit. Okay, we can simulate this. Later on I will show you how to simulate this, and you can check it for yourself. What code that you write, is it working? And it will work exactly the same inside a PLC. So there's two ways to do this simulation. One is to use, we can create these buttons in another page, visualization page. Then from there we can trigger the buttons, and we can check the behavior of this code. Another way I'm going to show you is a simple way to do it. So let's get into that. So if you log in, you're gonna get some alarm. You're gonna get some alarm or error. Okay, because we have not select simulation mode. So let's do that again. Okay, now then it is the program is correct. It can compile properly. Now we can run it. Okay, what we can do is we can select this start PB. We can go here and we can write values. So first of all, you need to double click. So once you double click, this signifies that we are going to turn on this start PB contact. So what we do is write the value. So as you can see, the output is turned on. Then what we do is we double click again, then we write the values. Okay, you see, so the program works as we intended, so it's holding it. So this is to like for start button for a production machine, to run a production for a machine. So we do that. So the production will start, commence. Then just say if we need to stop it, then we turn on the stop push button, double click on it, and after that we are going to write values. So you can see that the start hold is now off. So far so good. So our programs works as what we intended to be. So this is how you do the so a short verification whether your programs runs as according to your logic. So before we move on, so I'm going to show you is the variable that within this rung will be actually reflected in this section, the upper fold here. So this is where all the variable would be contained in. Okay, let me show you one example. We'll put in one normally close contact, then we call it alarm triggered. Okay, alarm triggered. Okay, see, so will be automatically added here. All right, so we log in, so it works fine. When you run it, so just say your output turns on, then something happened in the system, like cylinder does not activate, or there's some timeout in the sensor. So yeah, you can use this as a trigger point to stop your production. So let me write the value. See, so this is what happened. Let me show you the programming environment, the IDE that we are going to use. So this is a complete development environment for PLC and visualization. It's a good approach, powerful IEC language. Use of the editor and debugging function is based upon proven development program of advanced programming language such as Visual C++. So let me navigate you. Okay, this particular area is the object organizer, and this holds your POU, program organization unit. This holds your data type. This is your visualization, and these are the resources where you can put in your global variables, that kind of stuff. And we have this status bar. This we have one window message window here, and the this is a variable declaration. This is all your menu bar and toolbar, and your project name will be on top of it. Okay, now I'm gonna show you another simple way of creating these buttons in a visualization page. Then we can test how this program behave. So let's dive into that. First of all, what you need to do is go to the object organizer, which is this side, and you choose the visualization tab. From here, you can just right click on it, then add an object, just create a name for it. Maybe you want to call it Visual Demo 1 example. Okay, now we can start creating our buttons here. So you just choose this, we choose a rectangle shape, then we make our button here. Okay, you can choose to move where you want it in the canvas, or resize your button as you intended. You can see all these, the grids are there, so your buttons will move according to the grid. You can latch this grid on off if you want to. Now we can add a tag or variables in the element. So the next step is you can select the element, right click, and you choose configure. Then you have this dialog box. Now we have this window. Then we can select text. We can write start is caps start button. You can change the color, and you choose color and then alarm color inside. So you choose the red color. You can choose any color you want, but for this illustration I'm just using red. Then we go to the variable, change color. We put in the change color PLC underscore PRG dot. So we can choose what variable that we want. Is start PB. Okay. All right. Then we copy this. We need to do one more. So we need to do one more at the input side. Choose toggle variable, paste it here, then OK. So let us just test for this. We can run. Okay, so it works. So our start button to our okay. So the visualization is working correctly. So all our variable settings are correct. Let us continue for the next button. So we can just copy this other one. Then we can name it the text we change to stop button. Then the color similar, or you want to change something else. Maybe the stop button is yellow. Then the variable is delete. Then we put in the then what we want is stop. Then we desktop.pb, then we copy this, go to our input, delete, and paste it here, then OK. So let us try to log in and run, and start button, OK, stop button. So this is how you do, simple visualization, or we can say effectively this is the HMI and this is your PLC. So when you create when you create buttons in your HMI, you probably create the same way. It depends. If you use different kind of HMI, then you have to check the syntax or the variables that allowed, the variables that shared between the devices. Another thing I like to point is when you're doing all these simulations, you can see at the status bar here, so it's showing online, under simulation, and it's running. So it's really correlating to whatever selection that you have done over here. So when you log out, so nothing is there. So when you log in, it's showing online, and then under simulation, you can log out and simulation off, try to log in. Yeah, of course, simulation is, if you turn off the simulation, actually it's looking for a PLC. So for this time, we are using virtual PLC, so to test our codes. So just turn on the simulation, then log in, and you can see this, then these two, online and simulation. Then when you click run, you can see it's running now. Then when you, yeah, as I illustrated before, when you start, then you can see the start whole output is turned on, and you stop, yeah, the start whole button, whole contact or coil is off. All right, all the videos that you've seen before, so you've been exposed to one programming method, which is the most common and classic style in industrial automation, which is a ladder logic. So it's part of the IEC 61131-3 standards. Also, besides any other form or languages. So ladder logic resembles electrical relays diagrams. So you can see these are relays. These are 4-pole relays. These are 4-pole relay. 4-pole relay means they has 4 points, 4 common points. So this is the relay. This is the base, push button. So you can see here. So this contacts resembles a relay. Here is a coil. This is the relay coil. This is the relay contact. So similarly for this relay, you can see that a lane, this one lane is one pole or one common. So this is a 4-pole relay. It has a normally open, a normally closed, and a common. So these are push buttons. So with push buttons, so this area, this contact, the symbol will be different, but ideally if you have a 2-pole normally open contact, you actually can use one side of it, connect from 12 volt to the motor, and the other side is from motor to the ground or to the 0 volt, or to enable this motor to turn on. Okay, another way, if you use relay, it's much more automatic. If you use relay, you can use two relay. So for this, I think you can use only 2-pole, which is a bit slimmer than this. Then for one direction, one direction you can connect between this and this, the other direction you can connect this and this, so the motor does go the other opposite direction. And when you turn off, if you disconnect the connection, so the motor will coast. So if you turn on, let's say you apply a 12 volt here and 12 for the other side, so the motor does not move. So this essentially is doing like a brake. Okay, so as I like to iterate again, so this is a basic relay control. We've got 4 relays: A, B, C, D, A, B, C, and D, and depending on which combination is energized, the motor will rotate either side, clockwise or anti-clockwise, or brake. So here is the truth table. As you can see, if you turn on, this will be a clockwise. So if you turn on B and C, anti-clockwise. If you turn on AB, it's a brake or stop, and or CD, it's a brake or stop. So this is the truth table. So ladder logic works by scanning left to right. The power flows from the left this side, then through the horizontal, the right side. So it depends on the condition. It only reaches the output coil if the logic condition are true. This is typically something like a relay connection, let's say at 12 or 24 volt ADC, and then will be the 0 volt. So the relay will be energized. So relay receiving. So this is how it works. So similarly, if you are doing relay wiring, so you will do this way. So the ladder diagram will look exactly like a relay wiring diagram. So it's just think of it, it's like a visual circuit. So contact represent condition, and the coil represent the output. Now when the contact on, so the power passes through. So now here's how we implement that logic. So we have some declaration here, clockwise, anti-clockwise, and we have this relay declared here. In the first rung, if clockwise is turned on, if the clockwise is true, then we energize relay, A relay. So if the second rung is anti-clockwise, it's true, then B relay. And we do the same for C relay and D relay. So this is a direct readable translation from the truth table and relay wiring, but built in software. So that's how we bring an actual motor circuit into ladder diagram environment software. A simple logic in the real world application. Before we were looking at the ladder logic control to control the motor direction using relays. Now let's look at the exact same logic, but we are using structured text, or in short form ST language. So ST is a bit high level language. It looks and feel more like traditional, programmer familiar with C, Pascal, Python. This will feel familiar. ST is all about logic written in code form. So like if then else or direct assignment. Like this example is a direct assignment. So you write exactly what you want the PLC to do, then it follows line by line. So here how the code will look like. You see there's an assignment. I mean all the declaration will be the same, but for the ST, so this will be the way that we assign. So um, whatever value this clockwise is, that will be transferred to this side. So you can see, okay, when clockwise is true, then relay A is true. And so if we're going to another direction, then the other B and D has to turn on. So yeah, as I said, I will show you how to create this code later. And we will simulate also all in one go. We will simulate all the all in the different languages. You can see it's readable, it's simple, and the best part is there's no click and dragging, so just clean logic. So just tap it in. Now this doesn't mean ST is better than ladder, so I like to put out there. So it's just different. So like personally, I will go for ladder. Some some instructions that require some computations, then I use ST. So it all depends. So it depends how. Ultimately, you need to know how fast you can do it and how efficient it is. I said, yeah, it works and then you can do it fast, then by all means you can do that. Some situation call for ladder, and especially for visual debugging. But when you want more complex logic, yeah, as I said, condition ST can be a lot faster to work with. So this next one is the SFC, sequential function chart. Similar to ladder, it's like graphical, visual thing going on. So it's a visual step-based programming. SFC is like like a comic strip, going down of a PLC programming. Each block tells a story step by step. It's based on graph set, so as a standard that helps describe what happens first, then next, then after that inside a control system. So the idea is each step represent an action or state. Example, motor on and wait and off. Transition is like condition that moves you to the next step, like a timer done, as when sensor detected. And together, steps of transition creates a flowchart of how your machine should behave. So in this example, we move on the init step. So where you clear everything, whatever variable that you need to clear, you just clear them. Everything happens in here. We move from the init step. Then we check for the condition in trans 0. Then execute the step 2, and so on. The transition action can be programmed in structured text, instruction list, or other supported languages. So it's quite, see if like you are comfortable writing in ladder inside of this step, yeah, you can might as well go on. So whichever that you prefer, which language that you inclined to. Okay, for this motor example, so this motor start, so it starts in init block, then if the condition is met, the motor will move forward. Then we enter the motor forward step, then wait for motor stop, then the reverse motor direction with motor reverse, and finally reverse stop here. So just like a storyboard of a clear timeline of action. So this is the next language, FBD, function block diagram. This is what programming FBD looks like in each run. It's another graphical programming language used in PLC programming, and it's especially useful. It's the same kind of visual that you get. Operation like those boxes. It could be those instruction. Each operation or logic can be connected in a way assembled in an electrical diagram. I'll give you an example later, making it this intuitive and those from an electrical or control background. There are many ways to structure program using FPD, but the example shown here is I think it's more than enough. Then I'll show you how to create one, how to connect, how does it so-called cascading to another block. So I'll show you, so at least you know how to do it for your own project. All right, next one is the a language which is not that popular, but maybe you prefer it. So it's let's talk about language that been around for a long time, but it doesn't have always the spotlight. It's called instruction list. It is exactly what it sounds like. So it's a bunch of lists of instruction, one by one, step by step. No graphic, similar much, I think a bit closer to structured text, but this is more primitive than that. Just straightforward assembly style, assembly style logic that gets the job done. One of the 5-part standard language in IEC 61131-3, irregardless of the popularity. If you're someone like who likes seeing logic flows like written steps and recipes, IL might actually click with you better than the visual one. Each line contains a single command like load and st, so followed by variables and constants. Okay, so better you add a command at the end, so it helps make the logic clearer, especially when you come back a few weeks later. Okay, this one goes everywhere, even in st, in ladder, whichever it is. So there is a way that you can write command rung, or you can write comments for each variables. Now our example is we name the variable so descriptive, so it doesn't require, but you can add a comment which you can elaborate what input does or where the input comes from. Here's a quick example. Okay, what's happening here is it will load value x1, then after that we will end it with x2, then finally we will store the results in var1. So that's it, clean and simple. Now I'll walk with you how to create each of them. So for the rest of the language, I will quickly run through with you. So now we're going to do this ladder program for this DC motor control. Just add a program and ladder. Just say yeah, DC motor, DC motor, DC motor, LD. Right. So now we got it. So we're gonna just name this variable clockwise. Right. So boolean output is, or maybe relay A. Next output, this is relay B. Contact would be anti-clockwise. Next file, relay C. This would be, yeah, just copy over. So these are the motor that we are going to code based on the hardware wiring of this motor. Then after coil relay D, then this one will just copy the whole thing, paste it over here. So we save it. So the ladder is done. Now what we're going to do is the structure text. We're going to add an object, program, structure text, call the same names. So DC motor, then we call it ST. So what we do now, we just write simple line. So we call it relay A, then assignment that we need to use, then we copy clockwise, then give it a space, let it be, and clockwise, copy, maybe just copy the whole thing. Then D is this. Yeah, we copy this. So you can save it, log in, yeah, run. Yeah, so you see it grayed out. So as I said before, you need to add in the main PLC program. You have to call this function. You have to call this program. So we're just gonna add two more blocks. All right. So we're gonna call him PC Moto LD. So this is what you do. You just press full stop there. Then you're just gonna call it. You can call what is the program that you on. Then this is done for done fine. Let us log in, run. So that. So for this, right? Okay, it works for the ST. Then just true, right? So yeah. So you have, if you want to do some interlock, you can do that also. So it's not that difficult. So once the clockwise is on, the other one, the anti-clockwise must be off. You can do that. You have to do that. So it's quite important. So you don't want to burn the motor. We're gonna write the ST code now. Sorry, it's not ST. SFC. SFC. Got it. Okay. So what we do is, yeah, get same variable, copy. All right. Gonna get after. So we right, then make after init, then we call it moto. Maybe we call it clockwise, anti-clockwise. Then stop, moto stop. Okay, stop. All right. Then maybe we can, yeah, keep it simple. Yeah, for the ladder. Out, paste. We can call it, this is under clockwise, then we call it clockwise. In fact, add another output. Yeah, this line not necessarily needed. So we need what? Relay A, and relay C. Let's take a look at the ladder. So relay C. Okay, got it. So clockwise. And, so this would be AC, then this is relay B, relay D. Alright, so this is what the, yeah, see, once you write a code, then it will be like indicate here. So we need to create a transition. uh, Here we'll clear all this. Maybe we can just copy the whole thing here, clear that. So when there's a transition, like maybe we need to make a variable. Yeah, start CCW counterclockwise. Stop operation. Copy the same thing. Maybe we make it true. So let's go back again. So we loop back again. Then wait for the instruction. Wait for the command here to stop and ladder. So maybe we try to use this truth table, either one of them. So the best the best we do it. Yeah, we'll turn on this C and D. We are connecting the 0 volt. So we do that, C and D. So just put your output here. Relay C, relay D. Alright. So this one would be just say for this example, not clockwise, it's not anti-clockwise. Then yeah, this would happen. For the init, maybe we'll just take it. Let's copy the whole thing here. Maybe this one we use ST. So just put it false, right? Copy and paste it off. Alright. This. Let's go there. Clear the action. So we can this one. Maybe we can take it out. We can add an exit. This one over here. Okay. So that means when you exit of this, you clear this variable. So over here you wait for this variable. We can just test it out. How does it try to compile? Problems. Oh yeah. Found the first problem. Visual. Then 6. Alright. So it's in init now. let's say, all right, clockwise. So you can see motor A and C is true. All right, then say, yeah, this one, yeah, let's say value, yeah, see, so quite fast. So these two become clear. You can actually put a condition here, retry or whatever. Right, what about this? Over here, right? Mhm. Then if stop, all right, goes back. So yeah, this is how you do it. So now you're going to do for the FPD, add object, program, FPD, DC, DC motor, FPD. All right. So you can add a box. Then here we can just copy this. All right. Hmm? Yeah. So before we forget, then we add it here, another box. Press stop key, FBD. Alright, then it's done 7. Alright, then goes assign. So this time we put 1 and maybe copy this. Another rung, we add a box, add another rung, add a box. Yeah, alright. So P1, so this one will be assigned to relay C. Okay, assign, assign, right? Let's see, okay, wait, so this one relay B, relay D. Alright, so anti-clockwise, copy and paste. Alright, let's start to compile this. Okay, run, and so blue color, yes. So this is how you do it for FBD. Alright, the last one that we're gonna do for this, actually there's another one here, so let me check it out later, then give it to you. This D auto IL. Alright, yeah, this one. Gonna steal this thing from here. Alright, got it. So it's LD relay A. Then we have LD, SD. We call it anti-clockwise, relay B. Alright, LD, SD. Call this one is relay C. So from right from clockwise, relay A, anti-clockwise. Alright, one more LD, SD. You just key in the number LD and then enter, then SD enters and you get it. Put a space here, anti-clockwise. Right, then it's relay B. Oops, sorry, cancel B. Right, let's log in, run. So just say clockwise, right values. The A and C become true. So this is how you do it for instruction list. Okay, next I'm going to show you how to control a simple DC motor control as I promised you, using another one more programming language. So I'm going to add in a new object, call it DC. So we're going to do CFC. Alright, select CFC. Alright, done. So we're going to borrow the variable from here. Any variable will do. Go back to the CFC, paste it over. Yeah, it's done. Save. Alright, so we're gonna start to add in our instructions. So you put in two of them first. Maybe one is N, another one maybe I want to use move. Right, so this one we put in input and we put in an output. Okay, then so this also an input, then an output. All right, so we know it's the clockwise goes here, relay all right, then same thing goes here, and then this one relay C. All right, so that's it. So there's one more thing that you need to add in here as an input also. So here, yeah, put in one, then yeah, I'll go back here. So then stop CFC. All right, now we are good to go. Right, all right. So then run it, write the values. Okay, right, we can continue now. So this one has the flexibility. You can just move the whole block over here. It doesn't really matter. So it's give you a kind of visual free-form language similar to FBD, but with more flexibility. Let me just add in another one. Let's add the anti-clockwise. So maybe we can just copy the whole thing, paste it. We call it right. Copy this to this. Then relay, so it will be relay B, relay D. All right, so it's all done. So another thing I suggest that you put this value instead of putting 1, just put this true or false. So be clear, see with this distinct color. So be clear for you for when you're doing troubleshooting. You try to simulate this for anti-clockwise and write values. Okay, you see something wrong with the code. So it's actually nothing wrong with the code. So I did a mistake, even a rookie mistake. So basically the run was not selected, or the PLC is not in run mode. Just activate run mode, then it'll work. All right. So this is how this whole thing works. And the return block is, you can see the return blocks is only available when I start to log in. All right, so it will be at the bottom of CFC diagram. It returns just exit the current block, and so it does not affect the outputs. So it's normal to appear in the simulation, just the default end marker. Okay, so no action required, right? All right, we're going to do a process for motor clockwise turn, anti-clockwise turn, then clockwise, then we pause it, then anti-clockwise, then we pause again, then we loop back and I reiterate again. So with that done in this main PLC program, in ladder program, and then we will declare our global variable. We use this global variable tag to drive each of the DC motor control that we have done in different languages. So let us test this, run, see, okay, step 0, step 1, step 1, step 2, step 3. So it goes in a uniform manner. You can check the variable over here also. So this is the init, then after that the clockwise, then pause, the anti-clockwise, and start init again, then so it'll cycle through. So that's why it's crucial that you have a simulation, that you can do this kind of test first before you actually test on the machine or on the ground. So now what we do is we will use this drive the motor. So we will create a global variable. So we go here, global motor CW, GBL motor CCW. Alright, so let's compile. So far it's good. Right, then we log out. GBL stands for global, so at least you know it's a global variable. So what we do here, we can make some changes here. Instead of using yeah, we add another one more rung here. After this, then we output. Right, copy and paste this one. Then we do the same thing For the clockwise, then we create new rung, copy and paste. Then we output and go back to the global variable. Just copy this paperback. Then yeah, all right. Let's run. Pause. Right. Next one. And after that, you pause. All right. So how can we use this to drive the rest of it? So just for instance, we use the ladder, right? So what we do is create a rung before, then put a contact, put a contact, then some will put an output and an output. So one output is this, another output is the anti-clockwise. Go to the global variable, then that is CCW, right? And we run, okay, clockwise and anti-clockwise. So this is how you do it, right? Then if it's for the let's pick an ST. So what we're gonna do is gonna assign this, right? Gonna assign this, and this. All right. See. All right. So let's start. Run. Check it out. The status here. Clockwise. Clockwise. Okay, you guys can try to do the rest of it. Put the SFC, so you can do that yourself, or yeah, I will show it to you also here, because the method will be a bit different. So yeah, let's do that. Maybe we can try the FBD, which is much straightforward. You can do that. So turn it off, run before, create up. Okay, and we put an output, sign, assign. So we assign a clockwise over here. So we can even move, just for the sake of showing different instruction. Test this one. Run. C. Right. Clockwise. Clockwise and RA, RC. Anti-clockwise RB and RB. Save this program. Instruction list. Instruction list will be load and store. Right. We store at here. Another one is LDST. Store at all right. This is what we do. So we're gonna load the variable again. Copy. CCW again. Run. Let's see here from the status. Clockwise, right? Anti-clockwise. Clockwise, correct relay. Clockwise, correct relay. Right. For the sake of easiness, I will just copy this to a notepad for me. Alright. So SFC, what we'll do is can do this one first. For then we assign an output, put an input, copy this, then you're gonna copy the global variable. Alright, so close this and add a rung before. And we put in this input. Let's copy the global variable. This is clockwise, so anti-clockwise. Right, close it back. You can use this instruction. And okay, this is your instruction. And CCW. Let's test this. Run. So clockwise. Yeah. Okay, another thing is that here, because we put in a stop, so we need to add in not and not. Okay. not CCW. Okay, let's try this. All right, clockwise and anti-clockwise. Look back, clockwise, anti-clockwise. Right, save this program. Then have last one is CFC. Okay, what we do here, we can add. Okay, and we use move. So this one looks similar to FBD. So we'll move the global variable. Put drag here, some space, put in another input, drag it here, change this to CW, right? So yeah, I'll just bring it over a bit, bring it over here. So it's a bit, it looks cleaner a bit. Then we put an output, right? So put an output. So for the clockwise, place this. We input this here. Then say login, run. Okay, have you got some value from this? How we do it step by step. So there's a lot of example coming through, real world example. You can model it and then you can use it for your own use case. So let's go into that.
All right, let's walk through one of the simplest and most real-world relevant automation example: a saw table powered by foot switch, protected by an overload relay. So here's the layout. You've got a circular saw motor labeled M1 mounted on a bench. The motor is wired through an overload relay, a critical safety feature, controlled using a foot switch. All of this connects back to the control panel where the PLC would typically reside. Now, this is fairly simple logic, so I'll explain here how the logic works. So when operator press down the switch 1, the circuit completes and motor turns on. But it only works if the overload relay is a normally closed state. That meaning there is no fault condition. If the motor draws too much current, say the saw jam or something wrong with the material itself, so the overload trips, breaking the circuit, which are immediately shutting off the motor. That protects both the machine and the operator. So why this is valuable in industry? So this example, a real automation building block. It may be simple, but this exact structure happens everywhere. Foot pedal controls presses, cutters, grinders, and other machinery in factories, workshops, and plants. So as a system integrator, or you which is some dedicated to make you as one system integrator, basically an automation house. So we design logic like this: safety, simplicity, and maintainability in mind. Let us, draw on a short program for this. So basically, you are just going to have one contact, normally open contact, normally close contact, and an out. You will call this one switch. This is the overload relay. The output is the motor. Okay, that's it. So now we are going to simulate this logic. So kind of will show you. So it's going to be straightforward. So I'm just going to log in, then run, double click on the foot switch, and just write the values. See, so straightforward. So if anything to happen, if there is an overload due to some issues with the motor or the material itself or the saw blade, then the overload relay will be triggered. So this is what happens. In this example, you can see I'm adding this code in the previous code, our previous example. So what I have done essentially is I have called this program in the main program. So this is what something that you need to know. So if you have in a program, there should be only one PLC underscore PRG. Should be only one. Yeah, the rest of it, it could be any module names that you prefer. For this training illustration, I named it as a control motor with the overload relay program. So without this, yeah, it will not work. If I can show you how that that works. So let me just log out, and maybe I'll just add in uh, always off. This is always off bit. Okay, let me just simulate again. Run. So when I write the values, you see the output does not turn on. So this is what happened. Why it's not happening? Because this particular run, this particular code has stopped to enable this program from running. So this is another thing that you can use, like in manual operation or certain operation that requires certain interlocks, like safety door or barriers, or maybe a certain process time. Then you can use this. You can replace this with your or with your interlocking tag. So just let me just enable it. Then you see the output motor turns on. Okay, just now we were using this overload relay as a safety. Another thing that which is important that we need to create. Because this layout is not exactly real world, so it has to have some sort of safety enclosure or barrier or safety curtain, which is essential for this type of rotating, especially especially when you're dealing with motor rotating machines where he has motor will heat up, the blades will break, scattered around, will hurt the operator. So having an enclosure is essential. In many factories, the saw or cutting area is surrounded by protective barrier of safety door. That barrier has a built-in safety sensor or limit switch. And here's why. If that door is open or the curtain sensor is blocked, the system immediately stop the motor to prevent accident. So we can simulate this by just adding another one more contact here, and let us test this. So turn on. Yeah, before that, yeah, we need to turn on this. Okay, and whenever the door is open, so the motor will stop. And another thing to point out is if the motor is put with the brake, it's better to get that type of motor, or a clutch type where a brake or clutch. So if it's a clutch essentially will when engaged it will drive the circular saw. Brake is on the other hand is when you cut off the motor power, the brake will engage. So normally the brake will simply will be like when powered it will engage. If not powered, it will disengage. It will make free. Another way is if you want to immediately stop, you can use those are normally engage type, or normally open type, or normally disengage type. So immediate stop, yeah, you can have those brake which kicks in immediately after the safety barrier is open, or the enclosure is open, or the curtain sensor is blocked. So you can do that. So it's much more faster because the motor will immediately will stop, so prevent the operator from from accidents. Irresponsible person, I should say. I do not to point out anything. So we just want to stop them from getting hurt. So this is a simple addition that could save someone's fingers, limb, or their lives even. So automation is powerful, but safety must always come first. So do take care of yourself. Here I've added one more timer. You can create whatever variation that you prefer. Like for this case, I've added a delay time about 1 second. So let me just simulate this. If someone, if you can see, okay, you can see that there was a delay turning on the motor. But as soon as your foot comes out from the foot switch, it will turn off. This is another safety thing that you can add in. If someone were to accidentally press the foot switch without ready, then you can use this. So you can do a lot of stuff like if the material that you're gonna handle, there's another thing is you can add in a clamp, material clamp. So that clamps when you press the foot switch, it opens. So when you release it, it closes. Or when you press it, it engage. So it depends on how you design it. So for this matter, I think for this you need to press the foot switch, then the clamp will activate. The clamp might have a sensor, will be in series in this line. So then only the motor will start to turn and ultimately cut the material. So a lot of things you can add in safety. I was just this is something that so that's why I'm sharing with you the enclosure, the clamping, the material clamping, all that good stuff. So when you design, please make sure that you talk to your team, talk to your mechanical team, talk to your electrical team, your safety team, then to do a good system, that saves lives at the same time, reduce the reduce the downtime at the same time increase the productivity for your establishment or company. Next, I will show you the simple HMI control to do the simulation. So previously we were just doing double click and then writing the values. So with this, the testing will be much more seamless. Later I will add in the trips. Uh, Later I will add in the safety door in it. Safety door, so we can immediately test the system, and you can showcase this to your superior. Okay, how your system is going to behave. Okay, we are here to create this visualization. An object is called it model control. Okay, so here we are going to create rounded rectangle, and write text HMI, and I will put it chop. Okay, then double click on it. Okay, next we're gonna add in rectangle switch. Okay, let me create over here first. Let me keep this one align. I'll bring it to the front. And go to the double click, go to the attributes, control. So we're gonna repeat the process for the rest of it. Another thing to add is we're gonna put it on the left then, and we create a few more. Copy and paste. So this is, you can call it all point. So change here as well. And alarm. And we can add another. Make it same line. Call it switch. And for this variation, we're gonna add another safety dot. All right. So for the foot switch, double click, we go into the color, and maybe we change we just use this amber color. Then we go into the variables and color change variables. Okay, now this is the program is, let me go back to this to see what it is called. It's called control. Okay, control, control, control. Alright, one dot. Okay, can select one. We need to copy this. We need to copy this. Control toggle. we're going to add in the we're gonna add in the trip. So this we're gonna add in another one, which is the trip. Okay, so maybe this one we need to put longer. We can make them a bit longer. So just pick the switch. I'm gonna bring in front, put it there. Okay, okay. Now we can bring trip. For the other, we can make another one instead of. We can just copy that. Yeah, let's copy this. Save along. We call it this. All right. So maybe this video will put it outside. Okay. So now let's check back all this. Okay, it's good. The trip. Check color. Now maybe it's red color. Variable. Yeah, just gonna copy from here. Let's copy it somewhere. Then create maybe I create that. I just keep this thing so easy for me to copy and paste. Right? It's just going to change the variable here. So this is strip. So we use all relay. Copy this input toggle paste here. Okay. Then we have the motto. Maybe it's green, perhaps. No. Variable is so we're gonna copy it. Motto. So for the output, you do not need to use the you do not need to use this. So just a variable and change color. That will do. So one more item to add in is the safety. Maybe we maybe we choose the yellow variable. Down and paste it here. Alright. So I think we have all that. We just arrange horizontally, then we just this which is not relevant. test. Even this also is not relevant for our test. Then let's test it out. Okay, it works. And now then run again. So it works. So the strip. So looks like we have not added the attributes here. Is the wrong? Yeah, it's the right variable. Let me copy it properly again. The color. Oh yeah, the color we not choose. Maybe we choose something different. The switch on, the delay, the motor on, trip, cut off the motor. We have the trip reset, torpedo, turn on, cut off the motor. So this is, you see how quickly we can do this verification rather than double click. It's just time consuming. So as I say, I want to teach you that to go very fast in this. Fast is actually the faster you go, the faster that you make money for your company. So the faster is your reputation in the company, and you retain and you progress well in the company. And at the same time, you progress well. Your confidence builds up. For better. All right. Next, in our practical example, the two-door interlocking system. So this logic is used in place where environmental separation is absolutely crucial. For example, in semiconductor clean rooms where dust and particles can ruin the wafer. In medical labs where cross-contamination must be avoided at all costs. In food processing and pharmaceutical line where hygiene standard is strict. And even in data center and high security zone. So how does it work? So this example, you see there's a door 1 and door 2. Here's the logic. Both doors start locked. You can only open one door at a time because these are two traffics coming in. For example, this door 1 is the entrance to the clean room. So what essentially happens is these both doors don't actually start locked. Okay, it is actually both of them is unlocked because we do not know the traffic that is going to come and which door is going to be open first. Say if a person is coming in from his office and going into door 1, and when once he opened this door 1, door 2 will be locked. Another guy coincidentally came and wanted to open that door. He cannot open the door because door 1 is already open. So this kind of interlocks is important just to prevent these two environments, to be exposed to each other. As I say, okay, you can only open one door at a time. If the door 1 is open, door 2 is automatically locked, and vice versa. I'll show you how to integrate the extra logic for blower, vacuums, and cleaning timer in the next session. Ready for it? Let's go.
All right, let's dive into the program of this. So essentially, I have two programs here. One is the simple version. So I'm gonna show you later how does that work. Then I have another version which is I have incorporated the vacuum and air blower. So let's start with this. Okay, run. So basically, at the initial state, this will be the state of the door switch. So that means door one will be closed, which is the door is turned on, door switch turned on, and then door two also closed. So say if someone were to happen to come from this door, then just write this value. So door two will be locked. So when door one is open, door two will be locked. Once they close it back, so once you close it back, okay, so this happens. So that means both of the door is unlocked. So we try for door two. So when door two is open, so you will lock door two is open, door one will be locked. And once it's inside, yeah, then both of them are unlocked. So they can just walk out from this passageway to the other door. All right, so I've done another program for this. For this, I've added some different instruction. Rather than using coil, I've used set and reset. Okay, set and reset. So this is how you, let me just in it all, log out. Okay, this is how you get set and reset here. Yeah, set coil and reset coil. Okay, all are similar. I mean, it's a bit different than the other one. Okay, whereby here is the cleaning start. Then cleaning, we put in about cleaning time will be about 5 seconds. Then once the clean is done, clean done tag will be latched on. Then once the door is closed, clean is done, then the door will be unlocked back. So see, here will be set, here will be reset back. And once another cycle, next cycle, when the door one or door two is open, the clean done will be reset. Okay, let's go and simulate this. Okay, say door one. This is the initial state. Initial state will be this. Okay, where both of the door is closed. Door one open. Door two will be locked. Door two will be locked, and once they go in and close the door, then the start clean will opens the door. The door two will be locked, and once they close, the cleaning will start. And after 5 seconds, cleaning ends. Both of the door is unlocked now. Okay, either way he can go back to the original door or go forward to the next door. Then we try for door two. Door one will be locked. Door two open. Door one will be locked. Once it's closed, clean will start. Cleaning process will start. Then with end, then both door will be unlocked. You see, there's the potential are endless. You can do a lot of stuff with this. You can do a lot of stuff with this PLC program. So I see I've started with just simple, Now with this, I think you have much more better understanding. I have not added other display unit like go to this direct, go proceed to next door, or cleaning process, or the cleaning process is in progress. All that we can use this to indicate in the HMI. So let me show you how we do that. Okay, we have a brand new canvas here. So let's start to draw our HMI. Let's call this door control system. Top. Right. Maybe we make it font size a bit bigger. We choose something like 24. That's too big. Never mind. We can just drag the size of this. All right. Then we do indication here saying that door sorry door open. Come on. All right. Make it front. Maybe we can make it smaller a bit. All right. Then we create another rectangle. We call it open door one. Then copy this. Yeah, put it over here. This would be door two. All right. So next will be, let's copy this. Next will be the status. Right. Let me make a different size. Square size. Call it text door one. Right. Oops. Right. Top. Okay. Now maybe we can put another box, but we can hide them. Variables. So this one will be the variable. Let's see. For that, we'll turn on this door interlock. Okay, we have this. Just simplify our HMI tag creation. Yeah. So it will be about right. Then I'm gonna create another one, which is unlock. Okay. All right. Both of them same side. Variable will be control interlock. variable choose draw allow dot, yeah, this is the draw, right? So let us test this, run it. Yeah, get the other. So about from this, okay. Well, draw, sorry about that, simple to draw, draw, alright, now, alright, but another one, this would be our input toggle, yeah, this is same, but draw two, draw two long. Go to the input toggle, paste it, alright, so just copy paste here, this one is draw two, right? This one will be draw two, input, yeah, draw two, test them, about toggle. Alright, let's see what is the variables that we're putting. Okay, the text is correct. Variables which is not important up here. Okay, we'll just put in toggle variable, which is draw switch one. The rest of it pretty much is not okay. You can do, and I mean, you are welcome to do much fancy design. So this is, I want to show you how you can take an idea, just create for yourself, and you can even create to show your team what actually you mean. So this is very helpful. All right, so it's fun. I think we do not need this. Delete the color. That part is good. Install to, that's good. Check this part. Okay. Dot log one is 0. All right. Okay. And some should be the opposite. All right. Okay. What about this? Dot to 0, and the unlock is okay, the opposite. Okay, let's run this. Then yeah, lock, unlock, lock, unlock. Right. So yeah, dot to, right. Normal case will be this two door is closed. So if one of them is open, then the other door will be locked. Okay, and door two is open, then a door will be locked. So just simply to show you, simulate, to illustrate what this logic means. Okay, all right. Okay, we just covered the how to write, simulate AC PLC logic, real world example, but this is just a beginning. Next module, I'm gonna go even more deeper. So you learn how to apply best practices to actual PLC HMI project, and make sure you don't just work, but work reliably. You'll get the real application, not textbook theory. You'll see how to simulate real movement, control with a precise timing, handle operator input using HMI button, and structure your code for easy debugging and scaling. I'll walk you through the setup too, how to link your button, indicators, alarm, and PLC tag in a clean and logical way. Worth mentioning, I've included the app, all the programs you see in this video, and much more. I'll send you everything. But before that, I'll show you how to troubleshoot automation system using PLC tool. You learn how to test your wiring, verify your input and output, and make sure the problem is not in the code, but likely you find it in the hardware. Let's be honest, if you ever blame a machine crash, it might have been your fault. Loose wire, dead sensor, bad I/O card. They all look like a bug in an untrained eye. That's why before deploying your code to the real PLC, you always have to do I/O check. It's a simple process that saves hours of downtime and your reputation. Take this for example. A door sensor flickers. Machine doesn't start. Boss say I fixed the code, but the problem is loose sensor wire. You spot in instantly when you simulate the PLC input. Why must you do I/O check? Avoid wiring errors before switching to run mode and prevent full system crash. Isolate and solve hardware issues early. Reduce fingerprinting between departments, software and electrical teams. Alright, some of you might be thinking, oh, I need to do I/O check. It's just a waste of time. No, it is not. So before switching your PLC to the run mode, so you need to verify all the inputs and outputs. So why? Because if you have any wrong wiring, missing sensors or faulty connections, the entire system will behave unexpectedly, even crash. You might think that it could be something wrong with your code, but actually it is something wrong with your connections. This helps to isolate the hardware. Another thing is that it helps to isolate the hardware issues that might look like a program bug. If you're in the field, I bet it will save you hours, or maybe days troubleshooting. So what is an I/O checking? So let's say if you have a sensor in your PLC input and an actuator connects to the output. So I/O checking lets you do two things. One, manually write values to the test output. So turning like a motor relay on and off. Another one to observe the input status, like checking the sensor signal reaching PLC. So next question would be, how do I do I/O checking? So there's three things that you must do. Okay, make sure you're already online with the PLC, which is your IDE, it is online with the PLC. Another one is you make sure that that means your PLC is not in the simulation mode. Okay, must not be in the simulation mode, and your PLC try not to put in run mode. Just leave it in the stop mode. Then from there you can do the I/O checking safely. So you can see this is what the input and this is the output. Alright, so this is the way that you write down your inputs and outputs, and this is how you command it. So it's best that you command everything and align it properly. It's good for you in the long run. Then it's easy for you to come back to the list rather than going back to your Excel sheet. You can go back to your variable declaration. Then from there you have a clear snapshot of everything. So how do you actually do an I/O check? So you can, for this example, you can go like to this. Once you log in global, go to your global variable where you put in all your IOs, because the one that this one is actually your, so you go to your global variable and then you double click, then you can go right or false. So you can just force the value. You will get something like this. So it's actually because first thing is if you're putting your PLC in run mode, you have some programs that will run. So by doing this way of forcing, it will skip your programming. But what I told you is you do not put your PLC in run mode. So it's just for your safety. Writing a value sometimes it doesn't work. So the best way for you is to force the value. So click release the force, release force. This method works everywhere. So regardless of whatever TIA portal, GX works, whatever PLC they use. So the declaration part would be different a bit. Rest assured that yeah, you need to do this regardless of what PLC you're using. It is a standard practice in automation. So if you're working with a team and it protects everyone plus your equipment, especially no, the programmers, the engineers, mechanical engineers, from being not only getting blame issues, whatever, but we don't want to jeopardize the project timeline. All right, now we look into the relay and PLC input. Okay, when working with relays and PLC input, you often have three important contact types: normally open, normally close, and the common. For example, this one coil, it has two gang set of contact, each with NO, NC, and a common. When the coil not energized, the NC contact is closed, NO contact is open. When the coil energized, NO contact closes and NC contact opens. We wire the relay NO common terminal to the PLC input. The relay coils driven by a separate PLC or maybe another interface with another controller. You can use it as that could be an example. Now observe the ladder logic behavior. When relay is off, for example, now we are using this timer. See, when the timer on, the normally open, switch on, the normally close is off. Check, is on, is off, which is the same thing. So when the timer is off, okay, you can this one you can reference this as a relay. Relay is activated. Okay, normally open contacts closes and normally close contact opens. This is most popular so-called diagram. This is most popular in ladder diagram. NC contact appears on by default when the relay is off. When the relay is energized, the NO contact closes, PLC reads as on, then the NC contacts opens, PLC reads as off. This is crucial for control logic, whether you want something to react to a power presence. Practice between the logic NO and NC in your program logic. You'll start to see how this simple contact, can be very useful in your automation system. Okay, this is the relay that we use. Okay, on the surface of this, you can see this circuit that being displayed over here. So we know that which pin, this pin associate with this pin associate with this socket. Okay, from here then you know. Okay, number 5, if you want an O, normally open, then you connect number 5 and 9, and you can see even at the terminal block where they have screws, the numbers associated numbers on the terminals, so you can wire it accordingly. If you want normally open, it's 5 and 9. If you want normally close, it's 9 and 1. So 9 is a common. Likewise for this, 12 is a common, 8 is a normally open contact, 4 is a normally closed contact, 13 and 14 these are the coil where you energize your 24 volt DC power supply, depending on what relay you're using, a 12 volt or 5 volt, 24 volt. So that one is for DC, or AC, then It could be AC 100 volt, 110 volt, 220, 240 volt. Okay, now understanding the sensor light on and dark on setting. Okay, a concept in sensor configuration, the difference between light on and dark on is especially important in working with sensors in your automation project. First, let's define these two modes. Okay, the light on sensor turns on its output when it receives light, and dark on sensor turns on its output when no light received. It's that simple, but it affects how your input logic works. This is a light on example. So the sensor is not detecting, so meaning that the light beam is uninterrupted, so or it's not reflected back to the sensor due to the sensing range, how well the sensor light is amplified. As a result, the output is off and the circuit remains open. So when the sensor is closer to the object, the light beam is successfully received by the sensor or reflected back. Now the object is within the sensing range. The light is reaching the receiver. The sensor triggered because of the beam reflected back. So the output now will switch on. Understanding the specification. So when selecting sensor for your system, refer to the manufacturing label or specification table. Something like this. This is just an illustration, could be different from brands to brand. Now selecting sensor for a system, it shows the model number. Okay, what is the operation mode? What is the control output? Is it a relay or NPN or PNP? And the sensing range and the output indicator. So some of the sensor will have two indicator. One is showing stability. Sometimes it will indicate in green color, and another one is to indicate the output. It could be amber color or orange color. So when you see this comparison table, then you know which one is for you to use. Depend on your application. Some of them are switchable for the operation mode, and it depends on your PLC system, what you want to use, NPN, PNP, or relay. You can use for both system. Sensing range depend on your application, how far the sensor should be from your object or target object. So this is you have to be careful. The sensor output indicator might not match your operation. So if your sensor is on, indicator will should. If sensor is on, indicator should light up. To avoid confusion, always test it in your circuit, or you refer to your application engineer, application sales engineer of the said sensor brand. So do refer with them, clarify with them before you make a purchase. So now basically you understand the key importance between the light on and dark on sensor. So choose the right one for your automation setup. Let's take a look at how the PLC input output connection, how it is wired. So this example is an Allen Bradley PLC. It's an electrical panel. All those wires are actually connected to a power supply, a breaker, a contactor, terminal block, and so forth. So those are essentially devices from outside of PLC. It's not something that you wire randomly. It's more than established standard that makes troubleshooting, maintenance, and upgrades much easier in the long run. This is an example of sensor connected to PLC. This connection is a NPN type or sync type. This is one of the most common wiring type. You can see that okay, this part is outside of this PLC. The PLC devices have, okay, you need to supply the voltage. Say for this example is the 24 volt common. So basically you connect the 0 volt or negative to the one side of the contact, so the other side is you connect to the PLC. So this one will be your label. Example, this is X1. This one will label your DC power supply, and on the common side of the PLC side, yeah, you will connect the plus 24 volt. So that would be your label. Okay, plus 24 volt, minus 24 volt, or 0 volt, and this would be your label of the I/O. Example, which I/O it is. If it's if the first terminal, that would be X0. The next terminal will be X1, and depends on how's the terminal grouping is for this PLC. Like for this one, it can be a 16 point, it could be a 32 point. Maybe on the CPU side, it has like 10 points high speed input. So it all depends on what kind of PLC that you use. So before you looking at the simple relay contact sensor, so now which is commonly in the field, which is a NPN open collector sensor. It looks a bit complex, but I show you if you understand, you can wire it in seconds and minutes. So this sensor uses an NPN transistor as a switch. So when the sensor detects an object or target, so the transistor conducts, then the PLC connecting the PLC input to the common ground. So that allows the current to flow and turning it on. So you see there's a common here, and the same common is connected to the sensor. So that means it will be a same power supply. It should not be a separate power supply. It must be a same power supply. If you want a separate power supply, then you need to use, yeah, you probably need to loop back the 0 volt. So at least all of them would have common. Or if you want isolation, so you can use relay. So really isolate it. Again, common is just a shard across all inputs. Sensor collector is connected directly to the PLC. So this would be a label. This would be a 0 volt symbol plus 24 volt. So whether you're wiring a proximity sensor or photo sensor or curtain sensor, if you would like to connect an NPN connection for your PLC, so you need to purchase an NPN type. So don't get it a wrong one. So make sure that you have the NPN or you have a relay contact. So relay you can connect them in NPN or PNP. So regardless, but for this, if you buy a NPN sensor, then make sure your connection is NPN for the PLC. So the NPN is this kind of connection. So once you wire up, so the PLC will light up input. So alright, we tested the NPN inputs. Now just we look at the outputs. So here's one of the common scenario here. So if you want your PLC to control relay, so this typically a relay load, a coil. In this case, we are using NPN type transistor output, so also known as a sinking output. So when this PLC turns on, the transistor closes the circuit, pulling the current down and activating the relay. This one does not have the it will look similar to our open collector, where this terminal will be connected to the common. So the relay coils acts as a load. So it could be, yeah, it will be controlling a motor, whatever it is, a solenoid or another, or it's just an interface to another PLC. Connect to a motor, so you better do a correct sizing. So sometimes it depends what kind of amperage is the motor using. So just do your sizing well. But if it's connecting to just a simple solenoid or PLC, yeah, to isolate, I think a common relay will do. If you're controlling, but if you're controlling a motor or what, you have to size the contact, what kind of amperage that it can withstand. Because if it draws too much current, another thing is that if you connect to a relay coil, make sure that you size it correctly on this part. Okay, because maybe in most typical cases, this sensor, this transistor type will withstand 100 milliamp. So if normal relay, general purpose relay, like OMO relay MI2N, MI4N, they will probably take out maybe 10 milliamps, so that will do. But if you have those bigger, if it's a solid state relay, then it'll be fine. But if you have those contactors, or you have those relay coils that really pulls 200 milliamps, then you will risk burning this PLC output point. So you can damage the power point, or maybe worse, you could damage the output card. Always make sure that your power supply priority is you connect correctly. So the load sits between the positive power supply and the PLC output. Once wired up correctly, this output will trigger the relay coil. The PLC logic tells it. Okay, depends on how you write the code. Test it carefully and check it will click or it will display the LED. Okay, for this LED load, the connection, you connect the positive terminal on the positive side. The cathode, you are going to connect to the PLC output terminal. When PLC turns on, so the internet transistor closes, so sinking the current to common, allowing the LED to light up. So just like same like the relay coil example, but this setup is also using the same NPN syncing logic. Power flows through the load, in this case through the LED, so it gets pulled down to the common. This is a simple way even to troubleshoot whether your output card is working. So it's not working, so you do not need a multimeter. You can use LED to confirm it. All right, let's flip the logic now. Okay, this is a PNP input connection. It's also called a source type input. This setup, you can see it is supplying a positive voltage to the input terminal through the sensor. So sensor, it could be a relay contact. So when it closes, so it sends the positive 24 volt to the input. Notice the common is now connected to negative side of the power supply. This is exactly opposite of the NPN syncing configuration. So when the contact closes, so the voltage flows into the sensing element. So PLC detects the presence of the high level signal and marks it as on logic 1. So say it's same with the NPN. So all the sensor devices should consistently follow the same sourcing logic, or else you get a crazy erratic reading. This method of connection in the previous NPN could be Japanese machine. This one is more like for European machine, but now we are so globalized. I don't think so. It's a big issue now. So customer would have to clear up with the customer what is commonly used, or the maintenance lead in their company. So we ask them what kind of machine or what kind of inputs they use. So they will say whether it's NPN or PNP. So based on that, we will just, as a system integrator, we'll just design the system in such a way. So this is a open collector sensor type. So when connecting the sensor to open collector PNP output to the PLC input, is what actually happened behind the scene. Inside the sensor, there's an NPN transistor via such an emitter tied. The emitter is tied to the VCC. So you're going to connect the power supply positive to that, the positive voltage rail, and the collector of it is connected to the PLC input. So this is your label. So you connect this collector to that. So that means when PNP sourcing, that means when transistor turns on, it supplies VCC through the load. In this case, the load is the PLC input. The sensor comes with the 0 volt terminal, so connect to the negative side of the power supply, and so is the PLC common. It's connected to the negative or the 0 volt. So when the sensor sends a target, The transistor will conduct, the positive voltage flows to the input, the PLC sees it as high, a logic high, then or input on your PNP PLC input card, which are built to detect sourcing signals, mean positive voltage applied to input pin. Another example is a photoelectric sensor, detects an object on a conveyor, PNP or collector output. When there is no object presence, transistor off, no current flow, PLC input. So as soon as the object detects, sensor turns on, sourcing the plus 24 volt to the PLC input terminal. As a result, PLC knows instantly part has arrived. Emitter side is connected to the VCC, which connects to the positive power supply. The collector side is connected to the input of the PLC. The 0 volt connected to the PLC common, even connected to the common side of the PLC terminal. So when controlling a relay coil is next example, okay, with a PNP PLC output, the output circuit is designed to source. Okay, you can see here we are source the current, delivering positive voltage to the load when this output PLC output is on. So PNP pushes or it sources positive voltage from the output terminal to the load. So the PLC output terminal is connected to the end of the relay coil. The other side of the relay coil is connected to the negative side. PLC common is connected to the 24 volt or the positive side of the power supply. So this ensures sourcing logic works as you wired. So the internal transistor inside PLC closes, allowing the current to flow from the plus 24 volt through the common, through the internal circuit, out through the output terminal, into the relay coil, and finally back to the 0 volt or the negative side, the negative terminal of the power supply, completing the circuit. As a result, the relay coil energizes, trigger the mechanical switching action, the relay contact. So let's say you are controlling using PLC as my example before, controlling a motor. Again, do check the coil rating of this. So this one typically can withstand 100 milliamp. That's it. If it's a relay, if it's a contact, it's a relay, then it's not a problem. 2, 3 amps, maybe 5 or 10 amps, depends on what PLC model that you bought. Yeah, it can withstand. But if a transistor, try to limit this coil, below 100 milliamp. So again, coil energizes. Okay, let's say you are using a contactor to control a motor. So the PNP PLC output, one side of the coil of the contactor, the other side of the coil is connected to the negative side. So the logic enables, so it will supply the positive voltage to the coil. So energizes the contactor, the motor start running. Output pushes the current to the load, returns to 0 volt. The common terminal is tied to the positive 24 volt. The output turns on, energizes there, drives a relay to power high power devices safely through isolated contact switching. So when using to drive an LED indicator, it's the same setup, follow the same sourcing logic. Okay, the PLC output is connected to the anode of the LED. So essentially the positive side of the diode. Cathode side of the LED is connected to the 0 volt of the power supply. Common terminal of the PLC is tied to the plus 24 volt power supply. So once the PLC output is on, current flows from the 24 volt through the common terminal, through the internal transistor inside the PLC, and out to the terminal and to the LED, and the other side of the LED is connected to the 0 volt. Finally down to 0 volt, completing the path. As a result, the LED lights up. So just say if you have you want to control a conveyor motor, at the same time you want to show a PLC logic will turn on at starter, simultaneously will line up LED, so giving some real-time signals to the operator. Simple but essential example, how to use PNP output to drive low current loads like indicator lamp or LED or even tower light. Alright, this example is the activate after either input is on. So basically it is just saying if either of this sensor is not on, though, like for this product, if it's standing up, then both of the sensor will turn on. If it's dropped, then we consider this one as a reject. This is a simple illustration how this reject station for automated quality control is being used. Okay, the system uses dual sensor, as I said here, as a defective to check for the defective item. When sensor one does not detect the object, but sensor 2 does, the PLC flags this part as defective. The conveyor moves the flag part to the next station, and the pusher will start pushing the reject item. The HMI provide some indication, a real-time status update like ready for rejection and rejecting. Allow the operator to visually monitor system decision. This logic commonly used in food packaging, bottling, electronic inspection lines to ensure quality product reach packing, and then there's no escapee of reject parts. So let me show you from the visualization perspective. So this is the conveyor. Okay, this is the programs that I've written here to do the animation. So if I select this to introduce a reject part, so the pusher is being notified, then the pusher is rejecting the part now. This is an important skill, and there's actually a lot of things goes into this also. How do you program, not only program, how do you wire, how do you, if you're using a cylinder, how the cylinder should activate, how it should, generally you should imitate something like an emergency stop. Emergency stop means it's always normally closed. So if the connection is broken, then consider emergency stop. There's something abnormal happen. So similar to this, so there's something that you need to do to not only on the program side, on the hardware side also. Normally what we do is we will always engage the reject cylinder forward. So what happened is um, the product if anything happened to the cylinder, just say cylinder is broken, not broken, just say the IO for the cylinder is not connected, or there's no power, or some loose connection, then the pusher will be extended. So whatever, even if a good part, so you do not want to risk the good. We don't know whether it's a good or a bad part, so we will do rejection. So later on, the QC inspector will come and check whether some of the parts in the reject bin can be rerun or repurposed back or introduced back to the inputs, or maybe they can rework. So this is what they do. So I already give you some backstage of that, what's happening in actual production line. All right, so next I'll show you how to write this code, how to write this visualization HMI. Should be a bit exciting than the previous simulation. All right, we're going to start this programming for this conveyor system with reject station. So let's do that. So first thing you're going to do is just name it any name that to describe the system. Conveyor reject station. For this tutorial sake, I'm just gonna name this. We still use ladder and program, then click OK. Alright, So this is okay. Next is what we do is we're going to introduce the sensor. So we call it this upper sensor 1. Then we're gonna introduce normally open one. Okay, these are the condition for reject. So we're gonna put in the output, which is the reject part, and then gonna add in another rung after. Then we normally close, and we introduce timer. So timer on, and we introduce another timer function block. We introduce T off. We're gonna call this on, then blink off. All right. Next rung, what we do is we're going to add in a box with enable. This one is I change this time to real. The output is time convert is in real. So you choose in real. Yeah, here. Okay, the T on block is it's a standard function used in delay, turning on an output after input becomes true. So how does it work? So the in is the input trigger and boolean, and the PT is the preset time, and the ET is the elapsed time, and Q is the output. Q is the output. The graph explanation is when in goes through, the ET start counting, and once ET equals to PT, the Q turns true. If N goes false before PT, ET resets and Q stays false. So in this example, there are three codes, three language explanation. BD essentially is ladder, so easily visually you can see with input within PT and Q and ET. So in IL instruction list, so this is the syntax, and for ST this is the syntax how you code it. Okay, the use case is simple in our use case, or in any other automation system. For example, delay the conveyor, motor start 5 seconds after part detections to prevent false trigger. So wrap up Tion is essentially a delay and debounce logic. The TOF is stands for timer of delay. Used in delay, the used to delay the turning off of an output after the input signal goes false. How does it work? Okay, it still has the same inputs as for the T on. So input PT, ET, and Q. When in is true, Q is immediately true. When in goes false, T off start counting ET. Q stays true until ET reaches PT. Then Q turns false. So behavior in the graph. So it shows Q follows in immediately after going true, then the in drops to false, Q remains true, and PT duration, which is delay, after PT elapses, Q drops to false. Coding example is the same thing in instruction list, FPD, aka ladder also, and structured text. So application idea perfect for delay off of a solenoid valve or conveyor stop timer when you want a component to stay active just briefly even after the input has turned off. Okay, before I move on, so you can see I added this block time to real. So this is essential for our animation. So it's used to convert anytime if you need to convert time duration like a timer ET value into a real number, a floating point value. This instruction is useful for math operation, HMI display, and calculation involving speed, distance, and percentage. Use it in our example, and other example would be like display time in seconds or fraction of a second, or you need to perform some calculation or arithmetic operation with the time values. Simple example. Another example would be calculating duty cycle or animation speed from timer values. So the like as for this, the input is the blink on ET. Say it's a value 1.5 second, then it will output that in a real number. The real number will be 1500, which is 1500.0 millisecond. So if you the results will be in milliseconds. Unless you want to divide it manually, you can divide by 1000 to get in seconds back. To wrap up for this is essential when you are mixing timer data with arithmetic or visual output. It helps to go beyond just on off. You want to build more intelligent and flexible PLC program. Okay, what we do now is going to put in the preset value, and another thing that we need to put in is box enable. So this one we are going to put IV vision. Okay, this is the constant. So this is the speed of your animation. So you got to put it in real. Okay. So next would be just put this one down here. Add another network. Then we're going to add in normally open, and we're gonna add in function block. Okay, which is trigger. We're gonna put an R trigger. So this is from the queue, blink of queue. You're gonna name it this one as, and I'm gonna put an output here. Call it, just call it false. And for the next rung is add a blink off queue. So we're going to add in function block. Then this is the falling trigger edge. We call it keep it simple, short one trigger, and we call this pulse one. It's a boolean. All right, so next is after we're going to use this pulse one we're gonna set, because we want to display the parts, so this is way how we do it. It's a boolean. After, let's make it big a bit. So yeah, change to step 5. Okay. All right. I'm not sure whether, okay, never mind. Maybe I increase back. Okay. Leave it as it is. So at least for some clarity for your for viewer. So we're going to put in normally close and normally open, and a normally close first. This is part 4. Then pulse. All right. So we have to add in a reset coil for part 5. All right. Next is add in a normally open and another normally open. This one is pulse, and part 3. Then the output will be set part 4. Okay. Then we're gonna add in normally open and normally close, which is part 3 of pulse. Guys, this program you can make it as simplified as possible, but I'm just showing to you, even though it's just long-winded or long route, but yeah, it gets the things done. Okay, so but you can make it more simplified version. So but we're just going to focus on the outcome, which is we want to display how the visualization would look like. We want to test the code, how the code works, flawless, that kind of stuff. You have to ensure that first. So just follow along this tutorial. Part 3, only close, then output. Okay, just copy this and then paste it here, or maybe you can just change the reset. Yeah. Then new run be part 2. All right. Then yeah, you can copy this way also if you want to. Okay, let's delete. Oh, let's delete. Right. This is set. In part 3 is set. Part 2 is off. Pulse. Okay. Then reset part 3. Then we have next one after you open part 1. We add in the pulse and reset part 2. And another network. We close part 1. Pulse and reset. part 2. Okay, and then we have this check part introduction. So copy, written somewhere. Okay, not good. Then copy this pulse, and this is essentially a set. This is part 1. Okay, then normally close. Good. Pulse, and that will be reset part 1. So next will be we open part 3. Part 3 with pulse. This one is output. This will be output set. Part 3 visualization. We have this 2, part 3, and another one will be pulse 1. Pulse 1, and this one is set visualization. Part 3 visualization. And this one will be true, and we are the output. All right, so I think we are done on this part. Let me check all the variables. Right, looks all okay. Right, we'll just compile this, and now we start. Next we'll start with the visualization side, HMI. Okay, quickly I want to share something here. I am going to add in one more rung here because I found out there's some glitches in the animation. So here is what we are going to do is gonna add in to this network. Then just create a race off. Okay, boolean. Then let me just copy this over here because we need a one shot from this. If we call it run pulse. Yes. Oh, sorry, it's not this. Okay, it's supposed to be the rising edge. So my bad. So I'm gonna copy this. delete this. Then we can just go there and yeah, change this to this and R. Work. Then there's an output. We need to use this output. Right, it's another boolean. Then we use this to set part number 5. So we put one all contact. Then we put in right. So this is what we need to add in. So just save this. Let me show you why it is important. Okay, let me start off with, say, without having this. So say we have contact. So this one means you will not trigger this from this R trigger block. So what happened is, let me try to simulate. Run. You see this part? So this is the glitch. Only for the first time. Second run, yeah, it works fine. So these are some of the things that you need to do. Some debugging, I should say. So you need to do. So yeah, just get prepared. It's never that's the cool thing about this. I'm giving you this platform so you can test it out. Really, in prior time you can test it out. So you don't. I mean, it doesn't caught up. You don't caught up with these surprises. So this is what important. Okay, just say if I were to change back this to C. Okay, then let me just log in and run. See, so the transition is seamless now. So that's is what yeah, I wanted to share with you. Let's get into the animation now. Go to visualization, add an object, just create this is for conveyor system. Alright, so start with this rounded rectangle, and we have another box, put it in front, so maybe send it back. Right, so conveyor system. Yeah, let's make it a bit, maybe make it bold, bigger a bit. Yeah, it's bold. Alright, okay. Then what we do is gonna draw a button here saying that text not good. Just the input or reject. Then we'll go to the input, toggle, yeah, this one. But okay, this is from the, let me try again. Dot, yeah, not good. And the rest should be good to go. And yeah, we draw the other parts here. This is S1, sensor 1. Alright, one, and then 2. Make a circular. illustrate sensor, maybe just putting inside color. Okay, that's good. Copy paste. Yeah, here just drag it. All right. Now we'll make the platform, conveyor platform. Let's change the color to brown. All right. Then make the we'll make the product. Okay, something like this. Stands. Okay, some maybe yeah, somewhere around here. It's laying down. Make another one. Yeah, I just bring it over here a bit. So this one we bring it to front, bring it to front. Just change this color to red. Check. I'll just put it here. Around here. We need to do some adjustment, guys. So this one is a good product. Change to this green color. All right. Okay. So we make a few of them. Right. And we'll make a few at the front. Okay. Make a few of them. All right. Before that before that we need to make the pusher. So let's draw a pusher. Like that. Change different color. Yeah. All right. Front. Send it back. Oops. Do front. Yeah. So I need to adjust. Yeah. All right. Okay. Longer. Also possible. All right. So you can see the pusher standing out. Save for a while. All right. So next will be small box here. Check this out. So now we are going to add the variables, invisible variables. Then we have what is that? Let me copy the PLC code dot search part number 5. Okay. Search part number 5. Okay. Part that. This is part number 4. It goes part number 4. Then we have the absolute move offset, because we're going to move in this one axis. Move X. Next part, we're going to name this part 3. This is part 3, okay. The absolute move dot X, okay. This is part 2. Part 2. And absolute move dot X, and one more. It's part 1. Part 1 absolute move. Okay, so now all is good. Check the reject. Reject will be, yeah, still remove the same axis. Variable will be part 1 equals to 0. So the same axis, X, part 2 equals to 0. Then this part 3 is variable. This is part 3, this visual. Part 3 visual, which is 0. We got it, then we can just test it out. Let's save, log in, yeah, run. Yeah, another one more thing that I forgot to put in. Log out. Let me check the program. Yeah, we have not added this. C is grayed out, so meaning we have not called that function here, or we have not called the program here. So what we want to do, right click, box is enable, then we call it this, right? And this is done 3. Done 3. All right. Yeah. Let's change it here. All right. Let me just compile again. Run. Check out the, yeah, it's moving. Yeah, it's all right. It's moving all right. So let me introduce, reject, turn it off. Alright, so we have to adjust the layers now. So let's just click in the front, this guy front, and this element also front. Let's test this. So it looks like it works. Alright, but for this, even for this, the good product also, we need to front. Maybe we have to do it front. And this one, yeah, it should be done this way. Save this program. There's some glitches here, so we need to adjust that. Right. So there's a few more things. I think another two more element I need to put in over here. So let's do that now. So let us just create a small box here. Then I change the color. Oh, sorry, adding. So this one is variable. It's called that. I need this. Copy the name. Dot object part. Then we need to put some logic into that. Then there's another one. Just copy this. It's a bit up. Let's move out a bit. Okay, should be fine. Maybe adjust this side. Yeah, in line with the, yeah, that should do. And we have to change this part. Change the color should be okay. Yeah, and then change the text. Change to red color. It should do. That part is okay. variable is, we need to change that. This is part 3. Part 3. 0. That should be okay. Oh, checks, I need just fully rejecting. Yeah, that should do. Save, login, run. It's not working, but yeah, it looks weird a bit. Let's do the adjustment now. Okay, I've gone to adjust this position here. In fact, I have added, yeah, this is supposed to be the sensor. This is just the indicator to show. Okay, let's move this thing back. Right, then we need to put a variable here saying, okay, the variable is, yeah, text display, change color. Dot, it is upper sensor, upper sensor 1, and this color, upper, it's lower sensor, 2. All right, what we do now is, yeah, so once it comes at this position, normal state, yeah, you need to change the color. The color when the color, there's an issue. Okay, sure. Okay, all right. Okay, yeah. Actually, I need to put in the logic. It's one more thing that not only the variable, so variable has to, yeah, 0. So 0. That should work now. So when we put in the, we introduce the reject. that top side sensor is sensing. So just it's not that fairly accurate because you can do a lot of stuff over there if you don't want to make it real, but just to indicate that. Okay, another thing is we need to bring all this especially this, bring to front, 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 bring to front, then bring to front. Okay, let's try now. All right. Okay. Right. So as you can see now, the alignment, the the transition is quite good. So this because after the conversion, this X mode is about 125. So what I do is I just move this thing about from here 1 pixel. You can see here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's about 120. Okay, it's actually 130, 130. That means 20, 10, which is 310 is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. So 130, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it has to be apart. So this is the part that you need to align. So there's no okay. You need to align that. That's the part. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So go back. Then from here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have to bring back a bit. Bring back this one step behind. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. 2, 3, 4, 5, 6. Somewhere around here. The last one. Just bring it in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's also the same. So the movement has to be, it looks, then the pixel it doesn't overlap. The product does not overlap. So this is what you need to do. All right. So let's try again. And So it looks fine. Looks like when you stop, it just goes front a bit. When or you can change this. You can change this formula to match it. What is the value that you wanted? You can change that. So don't overcomplicate it, or the way that I did. Or yeah, you don't need to overcomplicate it. Just change this one. That should do to fit your what is your pitch. What is your pitch move? So yeah, that's it. So let us test one more time. So once the sensor sense over here and it stopped, then it indicate that yeah, this is not sensing. So the next station is ready for rejection. So rejecting section happening. All right.
Over the last few hours, you've just seen the tip of the iceberg. We have worked with PLC and HMI, starting from simple code and visualization, explore 6 different programming languages from instruction list, ladder, ST, FBD, SFC, and CFC for controlling DC motor, and also added a global process control. Implement safety for hazardous tools like table saw, control clean room environment to prevent contamination, simulated an assembly indexer, machine with a reject station. We also covered IO check where it's important for during the PLC test phase. We also looked at NO and NC, normally open or normally closed contacts outside the PLC program. And even we touch on the input and output sensing and switching for PLC. So you have seen what's possible from coding and simulation to taste of hardware, from concept to working system. Now here's the kicker. What you've learned so far is just the beginning. I'm going to give you an access to the real insider skill, the kind normally kept within the inner circle, working on top secret projects for Fortune 500 companies. I'm going to be teaching you a high level skill set because in automation, the bigger the problem you solve, the bigger is your paycheck. And that what you learn inside the 30-day automation challenge. This is where you get the blueprint to design program wire test fully functional automation system from blank canvas to dynamic tested simulation. In this challenge, you will learn to design electrical power, electric circuitry, plan control panel, and even design control panel. You will draft all this in CAD, design and assign PLC IO, choose and program PLC and HMI, run full system simulation that are 80 to 90% ready for practical implementation. It's perfect no matter you are a beginner, a technician or engineer who wants to create a portfolio system that to impress your client, win contracts, land job, and gives you the skills to actually deliver. In just 30 days, you won't just understand automation, you will prove it, you can build it. That's the difference between waiting for an opportunity and creating one. So if you found value in this free training, the 30-day challenge will absolutely blow your mind. Click the link in the description or in the pinned comment, join the challenge, and let's start building your automation system.